All right, today we're going to talk about friction. Now, friction is a force, and all forces are measured in newtons. But again, there's all different types of forces. So friction, the force that opposes the relative motion of one body over another. So an example of that might be, in here I have different surfaces, and here I have a block, so if the block was moving over the surface. So there's contact between the wood and, in this case, the rubber. So friction can be either useful or harmful. Now again, because friction's a force, the unit is newtons, and the symbol that we're going to use in this class is F subscript F. So we're going to use F for all forces, capital F, and we're going to use subscripts to differentiate the different types of forces that we're going to learn about. So useful friction, it can help us because has anyone ever walked on like ice and it's really slippery and you fall? So sometimes friction can be good to prevent you from falling. So when the roads ice over up north, they put down salt to kind of melt the ice, but sometimes they'll put down like gravel or something else to help. What some people do is they carry like cat litter or something like that in their car. So if their car gets stuck in the snow or the ice, it creates friction between the tire and that smooth surface. So, and again, there's good and bad types of friction. So other good types is our atmosphere creates friction in the air. That's more of a drag force. And when different meteors come from space, a lot of them burn up because of that drag in the atmosphere. So there can be, again, harmful friction that causes things to move out. So in your car, a lot of times they'll use different types of lubricant to make it smoother, to reduce that friction so things don't wear out. So you have like oil when your pistons are going up and down in your car to prevent it. My key was getting stuck in the lock the other day, so I sprayed a little like silicone type of lubricant in the lock, so now my key goes in and out easier. So heat caused by friction reduces the efficiency because in a lot of machines, heat causes things like metal to expand, and then when it expands, it's not going to move easily like a piston and engine and stuff. So in this class, we're going to be talking about different types of friction when we have two surfaces in contact with one another. So static friction, this is the friction between two surfaces in contact when it's not moving. And then sliding, or what they call kinetic friction, means it's already in motion. Let's say I was going to push on a box. So let's say, now I'm talking about like a big box like I was moving. So let's say I was pushing on a box to get it moving. If I'm pushing, trying to get it started, it feels like I'm pushing really hard, but then once it gets moving, it seems easier as it's going along. And that's because static friction is usually actually greater than kinetic friction. So if you've ever tried to push something, it always seems harder just to get it going, but then once it's moving, it seems easier to keep it sliding. And that's true. So this is something that's already moving. The coefficient of friction, this depends on the nature of the materials in contact. So the symbol for the coefficient of friction is a Greek symbol, and it's pronounced mu. And see the little symbol here? Okay? And it has no unit. So mu sub S stands for static friction, and mu sub K stands for kinetic. So again, this is to get it started, and this is once it's moving. Now, this is going to change depending upon the nature. So here, and we're going to use these when we do a lab, we have cork, rubber, sandpaper, and cardboard. And when I'm pushing this block with the same force over these surfaces, it's going to be different just because of the nature of the wood in these different surfaces. So mu is always going to be between 0 and 1, and here's some examples. So steel on steel is 0.57. Teflon is that stuff on the inside of frying pans, like when you cook eggs, and it doesn't stick. So do you see how the Teflon is 0.04? It's hardly anything. Rubber on concrete is 0.8. Rubber on concrete, when it's wet, is 0.25. So this is dry and this is wet. So this relates to the car when you're driving, the tires on the road. How many of you have your parents said to you when it's raining out and you're driving, they're like, slow down because it's raining, leave a larger distance in between you and the car in front of you? Well, physics-wise, that makes sense, because if the roads are wet, the coefficient of friction for wet roads is a lot less than dry roads. So for some of the equations that we've already learned, like the stopping distance, like you put your brakes on, how long it takes you to stop, this is going to change considerably if the road is wet. So you really do need to leave a larger distance. So static friction is always larger than sliding friction. Friction does not depend on the areas of contact, the surface areas. So mu, the coefficient of friction, is equal to F of F over F of N. So this is equal to the force of friction divided by the normal force. Now, I'm going to teach you step by step how to work problems involving friction. What I want you to do is do the steps that I tell you, and then there's never going to be a question is, what do I have to do next? So in every problem, we're going to sum forces. We're going to sum forces vertically and horizontally to the surfaces in contact. So remember, this is a summation sign, and when we sum forces, we're going to use the equation summation of F net is equal to MA. Now, there's two types of things we have to be careful for when we look at problems. Number one, if it's moving at a constant speed, that means the acceleration is 0. If it's accelerating, then we know that F is equal to MA. So we're going to look at two examples. So the first example is when something is moving at a constant speed. So again, we're going to write our given. We're going to write what we want to find. We're going to draw our free body diagram. And then we're going to look at certain steps to help solve the problem. So it says a horizontal force of 18 newtons. So a horse is necessary to pull. So remember, when we read problems, we're going to chunk it. A push or a pull is an applied force, so I'm going to write in my given FA is 18 newtons. A 52 newton sled, well, that's how much a sled weighs, so that's the force of weight. At a constant speed, I am going to write constant speed in my given. And the reason I'm going to write constant speed is, I'm going to write constant speed because that means the acceleration is 0. What is the coefficient of friction? So now I want to solve for mu between the sidewalk and the metal runner of the sled. Now, first of all, whenever I draw my free body diagram, how do I know which way is the sled going? Is the sled going to the right? Is the sled going to the left? I don't know. So I'm just going to arbitrarily choose a direction. Now, because we're going to be using the standard Cartesian sign convention that up and to the right is positive, I'm going to make right positive and I'll make left negative. So my applied force is going to the right. My frictional force always goes opposite the direction of motion. My force of weight always acts down, and then my normal force acts perpendicular to the surfaces in contact. Now, for tonight's homework, all the pictures are going to look like this, but guess what? You're going to draw it on every single problem. How do I know where to start? Well, when you don't know what to do, you go to the end. They want me to solve for mu. So the first thing I'm going to do is I'm going to say to myself, what do I know about mu? Well, I know mu is F of F over F of N, so I'm going to write that down. Then I'm going to say, do I know F of F? No. Do I know F of N? No. So because I don't know these, I know I need to solve for these. On every single problem, there's three things you're going to do. You're going to sum forces vertically, you're going to sum forces horizontally, and you're going to use the mu equation. You're going to do that for every single problem. That's never going to change. So if you do it in the wrong order, then you just do that. So don't tell me that I don't know how to do the homework, I didn't know what to do. You're going to draw your free body diagram, and you're going to do these three things on every problem. Okay? All right, so if I sum forces vertically, first I write my sign convention, up is positive. I'm saying summation of F of Y is equal to MA. Is the block accelerating vertically? It's not even moving vertically, so this is 0. So these, I look at my free body diagram. I am now going to add up all the forces going in the y direction. Fn is up, so it's positive. Fg is down, so it's negative. So Fn minus Fg is equal to 0. So Fn is equal to Fg is equal to 52 newtons. Now I'm going to sum forces horizontally. Summation of f of x is equal to ma. Is this block accelerating horizontally? No, it's not even moving. So this is also equal to 0. And then what forces do I have going in the x direction? I look at my free body diagram. This is positive and this is negative. We don't memorize. Obviously today we're starting with the easiest type of problem. But then we're going to get to ones where the pictures aren't going to be the same. And the only way to solve these problems is going to be by your free body diagram. So now FA is equal to FF, which is 18, and then the last thing I do on every problem, number 3, is I do the mu equation. So mu is equal to f of f over f of n. My newtons cancel, and I end up with this. And then I'm going to say, is this mu between 0 and 1? Yes, it is. Okay. All right, the next type of problem we're going to do today is for something that's accelerating. So, again, we follow the same steps. What we do is we read the problem, we write our given, we do our free body diagram, and we're going to do the same steps. We're going to sum forces horizontally, we're going to sum forces vertically, and we're going to use the mu equation. Do we necessarily have to go in that exact order? No. So if you don't have enough information, you go back and you do something else. So it says a 12-kilogram sled. This is the mass. So be very aware of these units, that this is mass and this is not weight. If I have the mass, can I find the weight? Sure I can. I can use the equation f of g is equal to mg. So I know I'm going to have to do that later. It's pulled along a level ground. The horizontal force exerted on the sled is 10 newtons, so that's my applied force. Find the acceleration of the sled if the coefficient of friction. So they gave me mu. So now I want to find the acceleration. So first of all, I can find the weight. F of g is mg. Now, I don't know where to start. When you don't know where to start, you go to the end. I want to find the acceleration. Now, which way is this block accelerating? It's accelerating in this horizontal direction. So if I don't know what to do, I look at my picture. I want to find A. So in the horizontal direction, I'm going to say summation of F net is equal to MA. And this net force is actually in the x direction. You know, we can call our net forces in the directions x and y. So F net is equal to MA. Now this is not 0 because I'm solving for this acceleration. Now what forces are going in the x direction? Well, this is where I look at my free body diagram. I have FA going this way, which is positive, and then the frictional force acts in the direction opposite of the applied force. So it's FA minus FF. When I rearrange this equation to solve for A, I see A is equal to FA minus FF over M. So I have FA and I have M. The problem is I don't know FF, so I can't solve this. So this tells me what I need to do next. This tells me I need to find F of F. So we know that mu is F of F over F of N. So F of F is equal to mu times F of N. I know mu, that's given in the problem. The problem is I don't know F of N. So this now tells me the next step. It tells me what I need to find. So the last thing and the only other thing I can do is I'm going to sum forces vertically. Summation of F of y is MA. The block is not accelerating in the y direction. It's not even moving that way. So this is 0. This now replaces this. So I look at my free body diagram. So Fn is positive and Fg is negative. And this is equal to 0. So Fn is equal to g is equal to 118. So once I get Fn, I then go back to this step. F of F is mu times F of N. I find F of F. And then once I get F of F, I go back to my original step and I say A is equal to FA minus F of F minus M. And I substitute and solve. So again, in these problems, I'm only going to do 3 things. I'm going to sum forces horizontally, I'm going to sum forces vertically, and I'm going to use the mu equation. And that's it.